record on this computer because now it starts recording now. All right, so we're doing this Gram-Schmidt procedure, three vectors that aren't orthogonal, and we want to make them orthogonal. Thank you for reminding me about that. Okay, so in any event, this would be a vector that is it's in the direction of the first vector, okay, and it has this particular magnitude. That's the magnitude being the projection of the second vector along the first, and we subtract it off from the second vector, okay? And so I maintain that vector is orthogonal to E1, okay? So this vector right here is orthogonal to E1. I'm going to normalize it, divide it through by its magnitude in order to get E2 prime, another vector. And E2 prime and E1 prime here should be normal to each other. If that's not obvious, let me give you a picture here in just a second. Okay, you take the projection of E3 then along the direction of E1 and E2, and you subtract that off. And again, we're using the projection operator in the same way here. There's E1, E1, and there's E2, E2, those projection operators we were playing with on the tutorial. You subtract those off, and I think E3, once you normalize it, is orthogonal, is perpendicular to E1 and E2, or E1 and E2 prime, the unit vectors in those directions. Okay, so that's the procedure. I'll show you the math here in a second, but first, I want to share with you my pen tablet and draw a little representation. Come on. Wow, we're being slow. Screen mirroring today. You gonna let me do it? Awesome. We're not gonna be able to do it. So I'll go to whiteboard instead. It'll be quicker. And I'll just have to draw it over here. All right, you're fired there, pen tablet. Okay, hopefully you're soon will be, yeah, you're seeing my my whiteboard here. And so I just want to picture two vectors. That might be what we were calling E1, and there's E2. Not perpendicular, right? That's the whole point. I didn't draw E2 nice 90-degree angle. I drew it right there. And so the step first says you want to normalize E1, okay? And so you create this little unit vector right here, E1 prime. And all that is you multiplied E1, well, you divided E1, multiplied by the inverse of its magnitude. You normalized it, okay? And so that was the first step. Then the second step was to find the projection of E2 along E1. So there's the projection of E2 along E1, right? That would be, let's see, we said E1 prime, E2, which is how you get the projection of E2 along E1 prime, and then it's in the direction of E1 prime, which is this thing down here, just the unit vector. So that's what that guy is, okay? And then the next thing is we say subtract that from E2, because I think E2 minus that guy, E1 prime E2 times E1 prime is this vector, and it's a lousy looking vector. I'm trying to draw straight lines with my mouse, not succeeding real well, but that's the answer. That is what this thing is that I just referred to, okay? And how do I know that? Well, I'm always troubled by doing vector subtraction. Instead, take this guy and add it to, what am I adding it to? I'm adding it to, let's see, I take that and I add it to that, and sure enough, I get that, don't I? So I always check vector subtraction by doing addition because that makes more sense to me, okay? And so, yeah, I guess that is the vector right there. Those two are perpendicular. They're like two components, right? That's how I find components. And so the next thing we do is we find the magnitude of that thing, and we divide the vector by its magnitude, and we refer to that as now not E2, but E2 prime, I guess, because we've created a perpendicular vector to E1 prime. Okay, and then if I want to do a third dimension, I can do exactly the same thing. Are you able to see that whiteboard? I don't see a rim around it. Somebody want to say yes or no for me? Go ahead, Peyton. Can you see it?
See, sorry, what am I looking at again?
Can you see the whiteboard with this kind of poor drawing?
Yeah.
Okay, because sometimes this is one of the inconsistencies of Zoom. When I share stuff, it usually gets a green bracket around what I'm sharing. I'm not seeing that right now, but I guess its own whiteboard it doesn't do that for, so it's inconsistent. In any event, I'm going to put this away, stop sharing that, and I'm going to go back to our notes. Okay, sharing that. So in any event, that's the steps. I normalized E1. Turning it into a unit vector, I find the component of E2 along E1, subtract that from E2, as that picture hopefully just demonstrated, that is orthogonal to E1 or E1 prime. I normalize it to get E2 prime. Now I got two vectors which are perpendicular, are normal to each other. I subtract the projections of E3 along those two directions from E3. I get a third vector which is normal to the first two. I got to normalize it to get a unit vector E3 prime. And we don't just have three states in Hilbert's, or three dimensions in Hilbert space. The reason I say and so on is because maybe you got a 9-state vector or something like that for whatever the system is you're studying. You can keep right on going as many different directions as you have for degenerate eigenvalues. You can create a set of orthogonal eigenstates from the states that work. All right, here's the example problem I want to do. All right, and I guess I need to, how come I can't advance my screen here? Do I have to stop sharing in order to advance my screen? Let's share that. And I want to, all right. Somebody has to explain to me why I can't advance my screen right here. I can do it now, and now I got to reshare it apparently. Yeah, discard that. Come on back. I think Zoom periodically just does that to mess with me. All right, so here's the example problem I want to do, which hopefully you're seeing in a second. I got two vectors, and you can see them up here at the top, F and G. And is it clear to everybody they're not orthogonal? If they were orthogonal, what would be the product of, I guess I'm writing F and G here. If they're orthogonal, we say F and G is equal to, and think about a dot product. Make them vectors F dotted vector G, because that's what this is, which remember is F times G times the cosine of the angle in between them, right? That's our definition of dot product. If they're orthogonal, what's the angle in between them? 90 degrees. What's the cosine of 90 degrees? 0. So the two vectors are orthogonal if their inner product, or their dot product, if you like, is 0. Okay, so is the dot product of F and G, or the inner product of F and G, equal to 0? Well, tell me, what is the dot product of F and G? It looks like 3 times 2, that's 6. And then minus 4 times 1, 6 minus 4 is equal to 2. And so, which is, in our case, they're equal to 2, which is not equal to 0. And so not orthogonal. So we've got to fix that. And that's what the Gram-Schmidt procedure is all about. The very first step is to take one of the vectors. I'm going to take F first and divide it by its norm, normalize it. If you look, the magnitude of this vector is 3 squared plus minus 4 squared, take the square root. And so that happens to be 9 plus 16, 25, square root is 5. And so if I divide F by its magnitude of 5, I get 3/5 I and 4/5 J. Okay, so that is the unit vector in the direction of F. Our next procedure said find the projection of the second vector G onto F prime, and of course multiply it by F prime as a unit vector, and then subtract that off of G. So I did that. I wrote, there's G right there, right? And then I took the inner product, the dot product essentially, of F prime and G. Okay, and so that's, I think I went 2 times 3/5. That's where I got the 6/5. And I went 1 times minus 4/5. I got the minus 4/5. 6/5 minus 4/5, I guess, is 2/5, right? Okay, so that's what I mean when I say that's it's just a number, in this case, 2/5. And then I multiply it by F prime, which is that guy right there. And so there's my original G, and I had to subtract off 2/5 times my unit vector F. So I multiplied it by 2/5. Let's see, 2/5 times 3/5 is 6/25, and 2/5 times minus 4/5 is, oh, I distributed a negative sign too, made that a plus 8/25, right? Common denominator was 25, and so this would be 50/25 minus 6/25, 44/25, and then this is, I guess, 25/25. Did I do that right? Hang on a second. Yeah, no, I'm good. 50. And then this is 25/25 plus 8/25. 25 and 8 is actually 33/25. And so that is the vector that is, I guess, in the perpendicular direction to F. But it's not normalized yet. Okay. So the next thing you have to do is you have to normalize that vector. It's a little harder to divide through by its magnitude than the nice one I picked with 3 and 4, which gave me a nice 5 because it's a 3, 4, 5 triangle. This is not that. I have to take 44 squared, 44 over 25 squared, and 33 over 25 squared, and that gets me the magnitude. That turned out to be 55/25. And then I have to divide that magnitude into the vector, and sure enough, I create a unit vector. Okay, that unit vector is perpendicular to that unit vector right here. Okay, so these two guys now are orthogonal. I just did 2 of them, but now as a check, are they orthogonal? Well, let's take their inner product and see if they're orthogonal. Then 3/5 times 4/5, which I guess is 12/25. And I multiply that by minus 4/5 and 3/5, which is also 12/25, but negative. And so sure enough, their inner product is 0, and the 2 vectors are orthogonal. And I've just done 2 dimensions of this Gram-Schmidt procedure. Last problem on the worksheet for this week is that, and I just wanted to show you, what do you do if the eigenvalues are degenerate, and as such, the eigenstates are not orthogonal, and you need them to be? And you can maybe ask, why do you need them to be? Well, because the only way you can guarantee that linear combinations of your eigenstates can create any other state in Hilbert space is if they're orthogonal. And so that's the reason why we need a Gram-Schmidt procedure. Everybody okay with that? Any questions before I go on? Because now we're going to talk about continuous eigenvalues for a couple minutes. All right, I need you to have a math fact in mind. And I want to remind you, back when we were talking about, I guess, the free particle the very first time, we introduced the idea of taking a Fourier transform, which is, I think, the top one. I call that the Fourier transform. You'll sometimes see people talk about FFTs, right? And so that takes either in X or T and converts it over to a function in frequency or wave number K, which sometimes people call the spatial frequency because of that. Okay, so that's a Fourier transform. On the other hand, if I started with the Fourier transform, I can do an inverse Fourier transform. The inverse Fourier transform takes me either from frequency omega or frequency K back to either time T or position X. Okay, and so that's what we have going on here. And you can do the integrals if you like, but I can tell you what a lot of us do. We go to places like Google or math handbooks or something like that, and there are tables that people have created. And remember, this is omega over here, but it can also be K. This is T over here. It could also be X. You can do in the time frequency or the position wave number K space, and those are equivalent. Okay, and the one fact I want to make use of right here is this row on the table. You could do the integral sometime. I would get a mathematician to help you. All I'm saying is, what if I do the inverse Fourier transform where F sub K is the unity of all things? Okay, and think about what you'd be doing. You're doing this integral from minus infinity to plus infinity, there's some issues with that because it's complex. And so what's the answer? Well, according to this table, the answer is the Dirac delta of x. So that's a math fact you need to have in place in order to understand a lot of what I'm about to talk about here, okay? And so I hope, you're not offended by the fact that I'm not actually doing this integral, that I did it by looking it up on a table, but I think that's probably what I would do if I actually had to do the integral anyway. I'd go to someplace like Wolfram Alpha and hope it can handle it for me. All right, and so the reason we need continuous eigenvalues, our experience has kind of been energy eigenvalues are often discrete, but other eigenvalues like momentum are often continuous, like the momentum of a free particle, for example. And so I guess my eigenvalue problem becomes the operator. This must be the eigenfunction that we're talking about. And my momentum operator, we've said over and over again, is just that, minus I h bar times the derivative with respect to x. And by the way, the little p right here means I'm talking about a momentum eigenfunction, because I'm going to have an f later on that doesn't have a subscript p. It's not for momentum. In any event, this is the eigenvalue then, okay, of the eigenfunction again. So the question is, what's the solution to that? And it was funny. I was a little bit disappointed because on this is just a constant, right? This is a derivative. On the first midterm, the solution to a first order differential equation was one of the problems on the test. I kind of figured it'd be a gimme and that everybody would just get it perfectly right. I was actually surprised that that people struggled with that a little bit. And so, your textbook doesn't solve this. It just puts it out there. Here's the solution. If I'm solving for what the eigenfunction is here, f sub p of x, here's the answer. And you could plug it back in and prove it's right. But I think a first order linear differential, in this case, is linear differential equation. The one I gave you on the hour exam on the midterm wasn't linear, but it was a first order differential equation. I just want to take you through the solution, separation of variables, and then integrating both sides. Okay. And I'm going to drop the of x, but I think this means that minus I h bar times df dx, right, is equal to some constant, which we're calling p, which is the momentum eigenvalue, times f again. And these are f sub p's, but I've dropped the subscript just because it's hard to write with this little pen. And so the technique to solve this guy is to separate variables, right? And so I'm going to leave on this side df over f, and I'm bringing that to the other side of the equation. And then I guess I'm going to bring to this side, well, the constant p is already there. I guess I have to divide through by minus I h bar. And let's see, and then I'm going to bring the dx over as well. So dx. And just, it's clumsy to have minus I h bar in the denominator. I think it's just as correct to have, oops, wrong thing. Where's my eraser? Do I have an eraser here? Do I have an eraser? Nah, maybe I don't. I got to just scratch that out then. I don't know. I'll find that eventually. IP over h bar times x. And what I've done is I've multiplied top and bottom by minus I h bar, right? Oops, by plus I. And then that IH minus IH bar right there, that cancels, goes to 1, and it brings the positive I up in the numerator. Okay, so once I've got it separated now, I've got df over f over here, and I got I momentum over h bar times x over here. The next thing I do is I integrate both sides, right? So the integral of df over f is the natural log of f. And let's see, the integral of, and that's a dx. The integral of this guy is I p over h bar times x plus a constant, right? All right, and so to solve for f here, which really, I said I dropped the subscript, is f sub p, I exponentiate both sides, right? So f here, which is really f sub p, and I'll write it now just to bring it back in, becomes e to the I p over h bar times x, I guess, and then this would be times e to the constant, which is just another constant, which I'm going to call A. Okay, so I'm going to put an A out here, and I'm going to get rid of that constant. And so that's why we say the solution is A e to the I momentum over h bar times x. And now the first question I'm going to ask you, according to de Broglie, what is momentum over h bar? And you should remember the de Broglie relationship is that the momentum is equal to h bar k. And so this would just be k, the wave number, wouldn't it? So whenever you see P over H bar, you can write K if you're lazy. Sometimes it's handy to leave it that way, and that's the way we can write it. We can simplify this by writing A e to the I kx, and we have at times, right? When a particle is scattering, that's exactly what we said the wave function was, and so this isn't incorrect. Now, as you can kind of point out, this isn't normalizable. This wave function here, this eigenfunction, is not normalizable. It's close, is what we say. It doesn't go to 0 as x goes to infinity, but it doesn't blow up either as long as the eigenvalue is real. And so that's the kind of the good news. We sort of say it's quasi-normalizable, or it's close to being in Hilbert space, because we need it sometimes. It was a handy thing when we scattered off, say, a finite square well. Yeah, we had discrete states inside the well, but outside the well, we had these scattering states, and they were important for us. All right, well, I guess I want to prove a couple things. I guess if the momentum eigenvalue is real, we get this thing called Dirac orthonormality, and I just want to talk about what that means. We said this is all predicated on the eigenvalue being real, and I just want to take the inner product of that wave function we just solved for with a wave function at another momentum. And so remember, this is going to be something, well, I write it out right here. I don't need to show you. Let's see, I took the A from both of them, brought it out front, and that's A squared. Remember, why is this a negative sign right here? Because although the notation drops it, the thing in the bra side is always the complex conjugate, okay? The wave function I just got is sitting right there, and I've got to go dx, okay? And so that's the integral we've got to do. And how do I do that integral? Well, first math fact I asked you to remember is this inverse Fourier transform when the function is just a 1 right here. And so I think I can do that integral with this form, almost like an integral table is what I'm proposing. And here's what I guess I have to do, though. In this integral right here, I'm going to make x be p minus p prime. Okay, so that's kind of a substitution to make that integral work for me. P minus p prime. Okay, and I think the other thing you'll notice is what's k in this integral is x over h bar. So my substitution to use that integral would be k is equal to x over h bar. If I made those two substitutions, then this integrand right here is exactly the integrand that I have right there. So I'm making progress towards using this integral to solve this one. Now you notice the integral I'm doing is over x. The integral that I've got tabulated here that I've used as a lookup, the math fact, is in k, but that's all right because I can take this guy and I can say, well, dk is equal to, I guess, dx over h bar, right? And so when I need dx, I just bring h bar to the other side of the equation here, and I can substitute in for dx, h bar dk. All right, great. The other thing I need is this constant right here. So if I jam in a factor of 2 pi, the h bar and the dk, well, I think I'm set. I've got the answer then. Then the answer is just the Dirac delta of x, remember x being p minus p prime. And so I've used this math fact in order to solve this integral. And it is a little weird because this one was an integral over x, and I'm using an inverse Fourier transform, which is an integral over k. But by doing this substitution, sure enough, it all works out. Okay. Now, to ensure this integral answer is normalized, it seems to me that I want this thing to be unity, right? Okay. And so a squared would just be 1 over the square root of 2 pi h bar. I square it, and this constant set out in front just goes to 1. And so we're saying that the overall wave function then must be that, because I've solved for what the constant a is. I've normalized it, even though we say it's not really normalizable, because the wave function itself, this eigenfunction, doesn't go to 0 out at infinity. It kind of did, as long as I accept that fact that the inner product of two states, p and p prime states, is this Dirac delta function of the difference between the momentum of the two states. And so we refer to this as Dirac orthonormality. It's not exactly the kind of orthonormality, that's hard to say sometimes, that we had for discrete eigenvalues, but it works for it. Compared to discrete, we said the inner product of two different states was the Dirac delta. And now we're talking about the inner product of two states as being the Dirac function, continuous thing versus a discrete thing. And you can see the work Dirac did in both areas in order to get the two functions named after himself. Any questions on that? So that's Dirac orthonormality. That's the best we can do for wave functions that don't have discrete eigenvalues, that have continuous eigenvalues. I do want to point out, though, that just like the discrete case, once you've got these wave functions, this f of p that I just figured out for us here a second ago, you can create any other state. Okay, it's just that rather than doing a sum like you do for the discrete case, you have to do an integral of this thing that's like a Fourier coefficient of the state. Okay, and so that's that principle still applies. If you're wondering, yeah, you can find this coefficient here. It's really not just a coefficient, is it? It's a coefficient function, is maybe the good description of it, although that's kind of an oxymoron. This function c, which is like a Fourier coefficient, but is a continuous function of momentum, you can find it using Fourier's trick, which is exactly what we did to find the discrete c's. Okay, you take the inner product of this function, and I usually put prime on the bra. Okay, and that's just to separate it out from a non-prime state on the ket. Any event, what that means is I go 1 over the square root of 2 pi h bar times the complex conjugate, okay, of the eigenfunction, and then I multiply that by a wave function. Okay, and we said that, well, we can express the wave function as an integral as opposed to a sum of the continuous wave functions integrated over momentum. Okay, and so right there I jammed that presumption right in there. Okay, and you notice I've got a double integral here. I've got one where I'm integrating over p, because that's how we define the function, and then I was originally integrating over x because I was doing the inner product. Well, you might guess I'm going to switch the order around here, and I'm going to take this guy right here, because remember, that's the notation which covers this, right? Because that's fp prime, and of course you have this right here, which is that guy, and then I'm doing the x integral because that's what the bracket notation tells me, and I'm just left with one integral of this c sub p thing, this expansion that I can do, integrated over momentum. Okay, well, Dirac orthonormality told me what the answer to that guy was. That's the thing that sort of takes the place of normality for a discrete function, which does go to 0 out at infinity. Is this as close as we can get here? We put that in, and remember how you do an integral with a Dirac delta in it. All it does is say wherever there's a p, you can replace it with p prime because I'm integrating over p. And so that means I just take the integrand and I substitute p for p prime. And so when I'm writing this inner product here, it does give me the Fourier-like coefficient is the result. And once you've got a result like this, you can say, well, that means that c without the prime is just equal to the inner product of f sub p, again, dropping the prime here with whatever the wave function is that you're trying to create. Okay, and so that's how you get these functions. We're going to give this thing a name on Friday, okay, because we're going to talk about the general statistical interpretation of all this stuff on Friday. We're going to, you can see that's, if you think about what we did here, we did an inverse Fourier transform, didn't we? Nope, we did a Fourier transform because we were integrating over X. And so this is the result of doing a Fourier transform. We sometimes give that a name, and we call them momentum function. In any event, eigenfunctions of momentum are sinusoidal with the de Broglie wavelength. I think that's what this tells us. No particles have determinate momentum. Instead, particles are represented by packets. That's what we would normally do with a narrow range of momentum. The eigenfunctions of momentum are not in Hilbert space, not normalizable, but this Dirac, the Dirac orthonormality provides us maybe a trick, a shortcut, a way to get around it and get quasi-normalizability so we can use the wave functions. These eigenfunctions don't represent possible physical states, but they're still useful for scattering, and we've seen that a couple times. Okay, I want to do an example, and then I'll quit here. And the example is, let's pretend the operator we're going to try to work with is the position operator. Okay, and so I want to find the eigenfunctions. I'm going to call them G this time. In fact, I'm going to call them G of Y. That's the eigenfunction. The eigenvalue is Y. It's just a real constant. And we're going to do this for the position operator. And so here's our basic eigenvalue equation. There's the operator, the eigenfunction, the eigenvalue, the eigenfunction again. And we're saying that that is equal to an eigenvalue Y. I'm sorry, this actually is the is the operator right here. The eigenvalues, we're going to call it Y, and that's why G is Y. I think that tells us we got to come up with a math function, this eigenfunction, such that the product of X times any function only gives you a particular constant Y times the function. And if you try to come up with all the math functions you know, there's really only one that will cause any value of X to be a particular value, X equals Y, and that would be the Dirac delta function, wouldn't it? Where the Dirac delta of the difference between X and Y. That would be something that just spikes exactly at the value of X where you want it, the value of Y. And so that's the only math function I can think of that could work. Okay, so what other things did we do? We wanted to see what the inner product of this function is for two different states, a prime state and an unprimed state. And so we go through the process we did on the previous slide. I put in this guy, the amplitude, it's squared. There's one wave function. There's the other wave function. In this case, the wave function happens to be the Dirac delta, okay? And so I guess if I do the X integral, I still get the coefficient out front squared, and then I get the other Dirac delta. I integrated over one of them, and the other one that caused me to substitute for Y. It caused me to substitute in Y prime, I guess, or X, it caused me to substitute in Y. Okay, so if I did this integral first right here, that means that X is equal to Y. I put Y in right there, and of course, that's why I get that as an answer. Okay, and so why not let Y equals 1 and just say that the wave function is normalized with that, and then Dirac orthonormality looks just like it did for the momentum operator. So any state can be written in this way, just like we said for momentum, and you can find the coefficient here, I guess, which we're calling Y. Okay, you can find it, and it turns out, if you look at it, it just turns out to be the wave function. So the eigenfunction is just a wave function. It's almost a trivial example, but it goes through exactly the steps one more time that we did for momentum so you can see it. Okay, what it all means. The wave function is really just a function that gives the coefficients expansion for the state in terms of position eigenstates, in this case, gx or gy or whatever we want to call it. We'll pick this up again on Friday. For operators with continuous spectrum, the eigenstates have real eigenvalues. They do form a complete basis, but you got to do an integral vice a sum in order to get any other wave functions. They have this Dirac orthonormality function, okay? And we say they're kind of not in Hilbert space. They're just barely outside, but they're close enough that we can use them when we need to. And that's kind of all I got here, unless you got any questions. Now, the thing we've got to do, now discard my annotations. The thing we got to do here, of course, is by Friday, complete the worksheet on observables as Hermitian operators. It's a little bit long, and I suspect people are going to need help. And so I did, as I said at the start, I want to set up a time maybe tomorrow or this afternoon, whichever is best for people, in order to work through them with you. Because some of them we've done, and you just have to rewrite what I done in the notes here in the last couple of days. For others, you may need me to help get you started. And of course, the last one is just an example. And so I'm going to call it quits here for today, asking you, please propose a time when we could meet. Probably tomorrow would be the best time for me. If you've got time tomorrow, when's the best time to meet to work through the tutorial on Hermitian operators? Anybody got a vote right now? All right. Well, if not, it's I'm letting you out a couple minutes early here, but that's okay. We'll be. Let me know when a good time for office hours is to meet to work on that worksheet. Certainly give it a try yourself, because a lot of it I have gone over here in the lecture today and in the lecture on Monday. This will be thanks to Jake, posted up on Canvas. Here in a second, I'll convert it to an MP4 and put it on my YouTube site so you can watch it. And that's about all I got. Everybody have a great afternoon. If anybody's got a preferred time, otherwise I'm just picking one tomorrow. It'll probably be in the afternoon, but I'd hate to sit right on top of some other class that you have with my office hours. So help me out with that.
Check the chat.
Check the chat. All right, hang on. Let me find the chat. Yeah, that's a good place to propose a time if that's what you're going. All right, so where do I see my chat here?
It's on the bottom of the screen for us where it says share screen. It's right next to it.
Yeah, I don't have that.
In Zoom.
Yeah, I'm in Zoom right now. Next to my share screen, I have pause, share, annotate, remote control. What else do I got?
It should be on the bottom of the screen.
Yeah, the host gets a slightly different thing. And where do I have my chats? I know there's a way to see it. Remote control.
You see the button to click participants?
Try Alt-H.
Alt-8?
H.
Yeah, but I don't have an Alt button because I'm on a Mac. Yeah, I guess I got the option. And you said 8?
H, like the beginning of hi.
Okay. Alt-H. No.
No. Okay.
Yeah, tried. It's a good try. Chat. There's a chat button. All right. All right. So there we go. I got tomorrow morning is a proposal. I got a 3. Is that 3 this afternoon, Jesse?
3 tomorrow.
3 tomorrow is good. Okay.
Yeah, I'm good with that.
3 tomorrow. If I could do 1 in the morning as well if that doesn't work for somebody. All right, let's go for 3 tomorrow afternoon then. That seemed like a little bit of a majority and we'll do an office hours right there to work on it. Nothing says you can't start it before then though, and so we'll be answering questions and helping you get through it so that we can get it turned in on Friday. All right. Hope everybody's having a safe and healthy time here at home. I'm kind of bored, but this keeps me engaged a little bit. Anybody gotten out and done anything? Anybody still working? And
Nope.
Never mind.
Nope.
Nope. Stuck at home, right? That's pretty much. I've gone to the store a couple times. That's really about it. All right. Well, you guys have a great day. And we'll see you. I'll schedule up an office hours for tomorrow at 3, and we'll work through some of that worksheet. Take care now. Stop share. And meeting.